Okay, so this is the circuit that is on slide 80 of the notes slideshow, and it shows a combination circuit with 3 resistors, R1, R2, and R3. And so I'm going to go ahead and work through this and show you also some things about how to more easily type this into the calculator. But I'm going to start by just writing the resistance values into my table that I have created here. And again, this is a good place to start. So I have my resistors, my 10 ohm, my 8.7 ohm, and my 5 ohm resistor. And we're just going to work through this problem and fill out this entire table for this combination circuit. Whenever you are solving this, we're going to start by getting the total resistance of the circuit. In order for us to do that, we need to first find the equivalent resistance for the parallel section of this circuit. Now the parallel section of the circuit is only this part right here. Okay, just those 2 resistors are in parallel, these 2 values here. And so if we're trying to solve for that parallel section, we're only going to add these. And when we use that find equivalent resistance in parallel, our equation for equivalent resistance in parallel is that one that's 1 over RT equals 1 over, in this case 10, plus 1 over 8.7. And in a lot of the ones we did in the notes, we're doing these by hand by finding a common denominator, but this is going to be a little bit trickier because I don't really want to try to find a common denominator between 10 and 8.7. You can if you want, but this is one where you might want to actually turn to the calculator instead. So I have a TI-84 here and a TI-Nspire here because it is a little bit different. Personally, I find it much easier to do on the 84 because it does have a really handy button I'm going to show you. Now you can type in your fractions, and I know you guys know how to do that. So you could type 1 over 10 like this, or you could enter it as a fraction. However, that's not the way I'm going to go about doing this. Instead, I'm going to use this reciprocal, this inverse button right here, x to the -1, because if I type in 10 to the -1 power, that is the same thing as 1 over 10, or 0.10. It's the fraction that we have here, okay, 1 over 10. And so that's how I'm going to type it on here. So I'm going to do 10 to the -1 power, that's 1/10, plus 8.7 to the -1 power, that is 1 over 8.7, and we're going to add those. And the answer we get is this 0.2149, it keeps going, but that is equal to this, 1 over RT. It is not equal to our answer. Remember, when we did this by hand, we then had to flip that fraction. We're doing the same thing here, but it's not a fraction. We just need to get the inverse. Yes, you can type 1 divided by your answer in order to do this, but again, there is a quicker way. So you can do that, or you can do this. Raise it to the -1 power, because again, that means 1 over this answer, and that's what we want to do when we flip it. And so that is the decimal equivalent for the equivalent resistance of that parallel section. So this whole section here has an equivalent resistance. I'm just going to label it R para of 4.6524 ohms. And again, I rounded that a little bit, but I carried out enough decimals so as to not introduce a bunch of rounding error, but of course I can always come back here on my calculator. Okay, the reason we need to do that first is because this whole section is in series with this. So when we go to find our total resistance, we're not adding this plus this plus this. We're adding the equivalent resistance for this parallel section, which is this value right here, with this value, because this is in series with this. And so if I add 5 to that, that is the value I'm going to use for the total resistance of this circuit. So 9.6524, I'm not going to be able to write all those digits, so I'm just going to write 9.65 ohms. So that is the equivalent resistance for the whole circuit. Okay, from here, we can now go ahead and fill in our voltage, total voltage. It's in the picture, 9 volts. And so we're going to label that right here, 9 volts. And I know that's my battery's voltage. I know this is the total resistance of the circuit. So with those two pieces of information in that total row, we are able now to go ahead and use Ohm's law, V equals I times R, and plug in these values. We're going to put our 9 volts here. We're going to solve for the total current by using that total resistance. Okay, and so if I want to solve for this value for I, I'm going to end up doing 9 divided by this answer. And so I'm going to do 9 divided by this 9.652, that value right there. And that is going to give me my current. And again, I'm using the unrounded value on the calculator, even though I'm writing the rounded value on the page. And so my current here is 9.324, and that's going to be in amps. Or sorry, 0.9. I just read that wrong. 0.9324 amps. Okay, so now we have our total current. Now that total current, as it flows through the circuit, and again, if we look at conventional current, it's going to leave the positive terminal of my battery. The charges are going to flow in this clockwise direction. It's going to split right here because I have a node, and part of it's going to go here and part of it's going to go here. It's going to come back together right here. And then I know that the total current flowing into a node or junction equals the total current flowing back out. So I come back together, I have my total current here. And so this resistor R3 also has this total current flowing through it. So I'm going to write it here as well. I'm going to write it hopefully a little bit neater. 0.9324. Okay, and so we have our total current going through here. But in this section it splits. Now these aren't the same value. If they were, it would split half and half, and that'd be easy. I could just divide it by 2. But I know that it's going to split, and it's not going to split evenly because my resistors aren't the same. I do know without doing any math that my charges, my current will be greater along the path of least resistance. So I know that my current will be greater through this resistor, the 8.7 ohm resistor, than through this one. Probably not significantly greater because those two values aren't exactly super far apart, but it will be different in those two. Okay, so if I want to go from here, we need to, we can't actually solve for those currents yet because before we can solve for these, we will need to figure out what these are, these voltage drops. Okay, and so we don't have enough information to get that, but we do have enough information to solve here. Again, this table is super helpful because you can see right away what you're actually able to solve for. And so I can go ahead and solve for the voltage here. Again, going back to Ohm's law, V equals I times R, I'm simply going to multiply this times this. So I'm going to take my answer and I'm going to multiply it by 5, and that is going to give me 4.662 as my voltage drop. I also know that the voltage drops along a loop will add up to the battery. This particular circuit has 2 loops. Some of my charges as they flow through this circuit are going to follow this path like this. And other ones are going to follow the other path that we see here, and they're going to do this. Okay, but on both of those loops, my voltage drops add up to the battery. So looking at this first loop that I drew, this plus this, there are 2 voltage drops have to add up to 9. I already know the voltage drop here, so this plus 4.662 has to equal 9. So that's super easy. I can find it by subtraction. 9 minus my answer gives me my other voltage drop, and that one is 4.338. And guess what? If you were to do the same thing for this other loop, you're going to get the exact same number because this is still 4.662. It's on a different loop than this one. These two also have to add up. So in that parallel section, your 2 voltage drops will be the same as each other, which is the same rule that we talked about with a parallel circuit. Okay, now they're not equal to the battery here, but they are still equal to each other. Now that we have these, we can work backwards to find the currents as they split. Again, going back to Ohm's law, voltage equals current times resistance. And so if I wanted to solve for the current, I would be doing voltage divided by resistance. And so I can take my answer that I have, I can divide it by, I'll go ahead and do this one first, 10, and I can get my current through that first resistor R1 to be 0.338. So 0.4338. And then through this one, I can do the same thing using these two values, or because I know that the current splits here, part of it goes here, the other part goes here. I could also find this by subtraction because I know the total current. So I could take this total and subtract this from it, and that would give me the remainder. But I'm going to go ahead and just solve it the same way I did this one, simply because I don't want to have to arrow up to find all those other values. So if I want to do that, again, I'm going to take the voltage drop there, which is this value, and I'm going to divide it by my other resistor, which is 8.7. And this one is larger, which we already knew. It is the path of least resistance, and therefore it does have a slightly greater current. This one's 0.499 as opposed to 0.4338. So 0.4986 if I'm writing the same digits, number of digits. Okay, so now we have our currents, and lastly you can find your powers. And power is easy because power, again, is just going to be voltage times current, and so it's just going to be this value times this value for each of them. And you can solve all of those. But before I do that, I first want to look at the Inspire calculator, because the equivalent resistance part of this is the part that I find so much easier on the 84, because again, remember, we were able on this one to do 10 to the negative 1 plus 8.7 to the negative 1, and then just take the inverse of our answer. And that's how we got that first value that we filled in, or we didn't actually write it in here, but this was the equivalent resistance right here. Okay, and this is super quick. However, the Inspire calculator, for whatever reason, does not have that button, and so we can't do the same thing. Instead, if we're trying to use the Inspire, we are going to have to type it in as a fraction. 1 divided by 10, and then 1 divided by 8.7. And yes, I know you can type it in as a fraction instead of like that. It does switch it for me when I press enter, but I'm adding those together. And again, it's the same thing we did here. 1 over 10 plus 1 over 8.7, but that's equal to 1 over RT. Again, it would be really helpful if we had that to the negative 1 power. You can, since you don't have that button, you can still use caret and then type in negative 1 to get the inverse, and that will work. It's just not as short, it's not as quick. Your other option is 1 divided by, and then getting that answer, and it'll give you the same thing, okay, because both of these are finding the inverse. And so that's what you need to do with these calculators. So if it's not a situation where you have a really easy common denominator to find, then I would recommend using the calculator, and you can type them in as fractions, and then when you get that answer, you can do 1 divided by it or raise it to the negative 1. Or if you have your own calculator, a TI-84 or something other than an Inspire, all of these other ones have this button, and this does make it super quick, because you can type that 10 to the negative 1, that's 1 over 10, that 8.7 to the negative 1, that's 1 over 8.7, and then you can also get the inverse of the answer using that same shortcut button. So again, if you've got it, I would recommend using the 84 over the Inspire for this, because it is just a little bit faster. Again, lastly, you can find all those powers. 0.4338 times 4.338. I did clear my history, so unfortunately I can't arrow up, and I'm going to have a little bit of rounding error in here, but hopefully not much since I carried it out to 3 decimal places. I have 0.4986 times 4.338. Okay, so those are my first two powers. The third one is 0.9324 times 4.6 0.662. Okay, and then I can also find the total power output from the battery, 0.9324 times 9. And so you can fill all these values in to each of these. Now, by the way, if these were light bulbs instead of resistors, one of the common questions you'll be asked is if each of these resistors is a light bulb, which would be brightest? And ultimately, it is the power that determines that. And so looking at these power values, not this one because that's the battery, but these first three, your largest or greatest value for power will be your brightest bulb. And so the brightest one would be this one, which it almost always is. The bulb that's in series is almost always brightest because it does have the total current going through it, and it usually also has the greater voltage drop because when you add them in parallel, it does decrease their resistance. Now, if these numbers are super large or something, then you may end up with some weird scenario, but it is almost always this one. But you can always confirm that by solving for the power if you're not sure. So anyway, that would give you your power for this one would be the largest. Again, that's the 4.3468, and that therefore would also be brightest. Okay, so that is how you're going to approach those combination circuits. So you almost always start by breaking down and starting with this parallel section, finding the equivalent resistance of that section, which we did here, adding it to this one to get the total so that you can then use the battery's voltage to get your current. Again, that current goes through this as well, so you'll notice you can put it there, and then you get to solve. And so you can find them pretty quickly like that. Hopefully that helps if you're having trouble with combination circuits, or if you just wanted to look at how you could use the calculator to help you answer some of these questions.